Welcome back to the deep dive. Last time we just scratched the surface of LLMs. You've got the basics down like tokens and embeddings, and that cool transformer architecture. But now let's get to the heart of it. How do these things actually learn?
Well, it's a fascinating process, really, and it all starts with a ton of data. I mean, a mountain of data. Think like terabytes of text. We're talking books, websites, even code. It's like feeding the model, like the entire internet.
Okay, so that's a lot of information. But how does a machine actually, how does it learn from just raw text? I mean, it's not like it's got a teacher correcting its grammar, right?
Exactly. That's where the two-stage learning process comes in. Pre-training and then fine-tuning. Imagine giving a kid a library card and letting them just roam free, just absorbing everything they can. That's pre-training.
So it's all about just like soaking up the patterns of language.
Precisely. The model is constantly trying to predict like what word comes next in a sentence. It's like playing this never-ending game of fill in the blank, and it gets better with each guess.
Yeah, I can see how that would lead to like a general understanding of language. But how do you actually, how do you measure if the model is actually learning, right?
Right. Well, that's where the loss function comes in. It basically tells us how far off the model's predictions are from the actual words in the text. So think of it like a scorekeeper. It constantly pushes the model to improve, get better.
So the lower the score, the better the model's doing.
Exactly. And to improve its score, the model needs to adjust its internal settings. We're talking billions of little knobs and dials. We call them parameters. And this is where the optimizer comes in. You can think of it like a clever coach that guides the model towards learning more efficiently.
So it's not just randomly tweaking those parameters. There's like a whole system in place to guide that learning process.
You got it. And the magic of pre-training is that this whole learning thing, it happens without any specific instructions or labels. The model just figures out the structure of language all on its own.
That's incredible. But I imagine training on such a massive scale, requires some serious computing power, right?
You're absolutely right. We're talking hundreds or even thousands of, specialized processors working around the clock for weeks or even months. It's a computationally expensive process, for sure.
So pre-training, it's like giving the model a solid foundation in the language. But what happens when you want to, teach it something specific, like writing different styles of text?
That's where fine-tuning comes in. So imagine now you give the kids specific writing assignments based on what they've learned from all those books. You might ask them to, I don't know, write a poem, maybe a news article, or even, code in a specific programming language.
So fine-tuning is all about tailoring the model's abilities to a specific task, right?
Exactly. And there are different ways to do this. One is supervised fine-tuning, where you give the model pairs of inputs and outputs, like for question answering. You feed it questions and their correct answers.
It's like giving the model flashcards to memorize.
In a way, yeah. But there's also instruction tuning, where you actually train the model to follow instructions. Think of it like training a chatbot to, respond to different commands. This makes it, incredibly versatile and much closer to how we use language, in the real world.
So fine-tuning really bridges that gap between general language understanding and like specific application.
Precisely. And what's remarkable is that even though the fine-tuning data set is much smaller than what's used for, pre-training, it can dramatically change how the model actually behaves.
This two-stage learning process is fascinating. We've covered a lot of ground already, from the initial data deluge to the nuanced adjustments of fine-tuning. But before we get too carried away, I'm curious, what happens when a model learns a little too well? Like when you cram for a test and forget everything a week later.
That's a great question, and it leads us to the concept of overfitting. Overfitting. Well, it's kind of like, when a student, they just memorize the answers for a test. They don't actually understand the material, right? I mean, they might ace the test, sure, but they haven't really learned anything useful.
Yeah, so it's like the model is like getting too focused on those specific examples that it's seen, rather than actually grasping like the underlying patterns.
Exactly. And just like that student who forgets everything after the test and overfit LLM, well, it might perform poorly when it's faced with, new unseen data.
That makes sense. So how do we know if a model is overfitting? Are there any warning signs, that we can look out for?
Absolutely. One way is to use what's called a validation set. It's basically, it's a portion of the data that's held back during training. Think of it like a practice test, for the model.
So we train the model on one set of data, and then we test it on this separate validation set.
Precisely. And if the model performs like much better on the training data than on the validation set, well, that's a red flag. It means the model is, likely overfitting and might not generalize well to new information.
That's a clever way to catch it early on. But what can you actually, what can you do if you realize your model is overfitting? Do you have to start the whole training process like from scratch?
Not necessarily. There are techniques to combat overfitting, almost like giving the model a study guide to help it learn more effectively.
Okay, I'm intrigued. What kind of study guide are we talking about here?
One common approach is called regularization. It's basically, like adding a penalty to the model's complexity. This encourages the model to find like simpler explanations for the data, and that often leads to better generalization.
So it's like telling the model, hey, don't try to memorize every little detail, just focus on the big picture.
Exactly. Another technique is to simply, use a smaller model. Sometimes a model with fewer parameters is less prone to overfitting because it just has, less capacity to memorize the training data.
Makes sense. So it's all about finding like the right balance, right? A model that's complex enough to capture the patterns in the data, but not so complex that it starts, memorizing everything.
You got it. And of course, having more data can also help. The more examples the model sees, the better it's able to generalize.
Right. More data means more opportunities to learn, like the underlying patterns, not just the specifics of individual examples. We've talked a lot about the training process itself, but I'm curious, what about like the resources involved? I mean, I imagine training these massive LLMs, it requires a lot of computing power and energy, right?
You're absolutely right. Training, especially, the pre-training phase, it's computationally expensive. It requires specialized hardware like GPUs or TPUs, and even then it can take weeks or even months to train a large model.
Wow, that sounds incredibly resource intensive. Are there ways to like make the training process more efficient?
Absolutely. There are a number of techniques that researchers and engineers use to optimize that whole training process. One approach is called mixed precision training.
Mixed precision training. What is that all about?
It's basically it's a clever way to reduce the memory footprint of the model. Instead of using 32-bit numbers for all the calculations, we can use 16-bit numbers for some operations, which saves memory and speeds up training.
So it's like finding a compromise between precision and efficiency.
Exactly. And then there's gradient accumulation, which allows us to effectively increase the batch size, the number of examples processed at once without needing, more memory.
Wait, doesn't a larger batch size require more memory by definition?
You'd think so, right? But with gradient accumulation, we process smaller batches and accumulate the information about how to adjust the model's parameters over multiple batches before actually like making an update.
So it's like combining information from multiple smaller steps before making like a big adjustment. That's pretty clever.
It is, and it can significantly speed up that training process. Then there's gradient checkpointing, another technique to reduce memory usage during training. Instead of storing, all the values used to calculate how to adjust the model, we selectively store some and then recalculate others when needed.
So it's all about finding ways to do more with less, right? Like reducing memory usage without sacrificing training speed or accuracy. Are there any other like optimization tricks up your sleeve?
Well, we talked about, optimizers earlier, and while Atom W is, pretty popular, there are others like LNB, which adapts the learning rate for each layer of the model, or, Sophia and Lion, which have shown some promising results recently.
So many options. It seems like choosing the right optimizer is a bit of an art form, depending on, the specific LLM and the task at hand.
You could say that, and this is an active area of research. So new and improved optimizers are constantly being developed. And spooting of improvements, there's this fascinating technique called knowledge distillation.
Knowledge distillation. That sounds intriguing. Tell me more.
Imagine you have a large, powerful model that's already been trained. We call this the teacher model. Knowledge distillation is all about training a smaller, more efficient, like student model to mimic the teacher's behavior.
So it's like passing down the wisdom from the master to the apprentice.
Precisely. The student model learns from the teacher's outputs or internal representations, essentially compressing the knowledge into a smaller package. What's remarkable is that the student model can sometimes outperform the teacher on certain tasks.
Wait, really? how is that possible? I mean, I thought the teacher model would always be like superior since it's, bigger and more complex.
It's thought that the student model benefits from learning a smoothed version of the knowledge, capturing the essence of what the teacher knows without all the unnecessary noise. And this can lead to surprisingly good results.
That's fascinating. It seems like there's still so much to learn about how these models truly like learn. But what about the problem of forgetting? I mean, if we keep training LLMs on new data, won't they eventually like forget what they learned before?
That's another great question, and it brings us to the challenge of catastrophic forgetting. Catastrophic forgetting. Well, it's kind of like when, you learn a new language and you start to forget words from your native tongue. It's a common issue with neural networks, including, LLMs. As they learn new information, they can sometimes overwrite or interfere with what they've, learned previously.
So it's like the model's memory is getting like overloaded.
In a way, yeah, and it can be a real problem if you want an LLM to be truly versatile and adaptable. Imagine fine-tuning a model for a new task only to find that it's suddenly like terrible at its original task.
Yeah, that would be a major setback. So how do researchers like how do they address this issue of catastrophic forgetting?
Well, there's a whole field of research dedicated to continual learning or lifelong learning, as it's sometimes called. The goal is to develop techniques that allow LLMs to learn continuously without forgetting previously acquired knowledge.
So it's like giving LLMs a more robust and flexible memory, closer to like how humans learn throughout their lives.
Exactly. One approach is called rehearsal. It's like periodically, revisiting old textbooks to refresh your memory. We can retrain the LLM on older data to help it retain that knowledge.
That makes sense. Are there other methods besides rehearsal?
Another approach is to use regularization techniques that specifically, protect the parameters that are important for earlier tasks. It's like putting a mental sticky note on those, crucial pieces of knowledge, reminding the model not to overwrite them.
So it's all about like finding ways to safeguard the model's existing knowledge while still, allowing it to learn new things.
Precisely. And then there are, even more sophisticated methods that involve like changing the architecture of the model itself, allowing it to grow and adapt without, overwriting previous knowledge.
It sounds like continual learning is a crucial area of research if we want LLMs to become truly versatile and reliable tools. But let's shift gears a bit. We've talked a lot about training, but most people they aren't building LLMs from scratch, right? They're using those pre-trained models that are already out there, like the ones powering chat bots and language assistants.
You're right. For most users, the real magic happens when you start, interacting with these pre-trained models, giving them instructions and seeing what they can do. That's where inference comes in.
Inference. It's like taking a trained LLM for a test drive. But I imagine there's an art to getting the best results. You can't just type in any random question and expect a brilliant answer, right?
You're absolutely right. That's where prompt engineering comes in. It's the art of crafting effective instructions or prompts to guide the LLM towards producing the desired output.
Okay, I'm all ears. What are the secrets of like good prompt engineering?
Well, first and foremost, clarity is key. Be explicit about what you want the model to do. Don't just say write something about cats. Instead, say write a funny short story about a cat who thinks it's a dog.
So it's about giving like specific instructions, not vague suggestions.
Exactly. And just like when you're, explaining something to a person, providing context is crucial. If you're asking the model to, I don't know, to summarize a news article, include the article itself in the prompt. Don't assume the model has access to, everything you've ever read.
Makes sense. So clear instructions, relevant context, anything else.
You also want to be specific about the desired output format. Do you want to list a poem, code in a specific programming language? The more details you provide, the better the chances of, getting what you're looking for.
So it's like giving instructions to a very literal-minded assistant, leaving no room for misinterpretation. But I recall there are like different types of prompting, right? Something about zero-shot and few-shot prompting.
You're right. Those terms refer to how many examples you provide within the prompt itself. Zero-shot prompting is like, it's like asking a question without giving any hints. For example, what's the capital of France? A well-trained model should be able to answer Paris based on its pre-existing knowledge.
So it's relying solely on its pre-training. What happens when you need it to go beyond like general knowledge?
That's where few-shot prompting comes in. Let's say you want the model to, I don't know, analyze sentiment, whether a piece of text is, positive or negative. You can provide a few examples within the prompt, like this movie is amazing positive, that meeting was dreadful negative.
And then you give it a new phrase and see if it can like correctly classify the sentiment. It's like giving the model a quick crash course on that specific task.
Exactly. And what's remarkable is that these few examples can, significantly improve the model's performance on that particular task. It's like fine-tuning on the fly, within the prompt itself. And then there's a chain of thought prompting, which can be, especially useful for tasks that require like reasoning or logic.
Chain of thought prompt. That sounds intriguing. Tell me more.
Well, instead of just, asking for an answer, you encourage the model to explain its reasoning step by step. So instead of just saying, 2 plus 2 plus 4, it might say, first we take 2, then we add another 2, which gives us a total of 4.
That's fascinating. It's like getting a glimpse into the model's thought process, which can be, really helpful for understanding how it arrived at a particular conclusion. This prompt engineering stuff is clearly a powerful tool, but I imagine there are challenges as well, right? What are some common pitfalls that people, run into?
One common issue is ambiguity. We humans are great at understanding nuanced language, but LLMs are very literal. If your prompt is even slightly ambiguous, the model might, misinterpret it and produce unexpected results.
So it's important to be like as precise and clear as possible, avoiding any language that could be, taken multiple ways.
Exactly. And it's easy to forget that LLMs don't have the same, common sense or background knowledge as humans. Another challenge is finding the right level of specificity. Too vague, and the output might be, unfocused. Too specific, and you might constrain the model's creativity or its ability to generalize.
So it's a delicate balancing act, finding that sweet spot where you're providing enough guidance, but also leaving room for the model to showcase its capabilities.
You got it. And it's important to remember that even with the best prompt engineering, LLMs have limitations. They can sometimes hallucinate, generate plausible sounding but false information.
Right. It's always crucial to be like critical of the output and double check facts, especially when accuracy is paramount.
Absolutely. Prompt engineering is an evolving art, and we're constantly discovering, new techniques and strategies as we learn more about how these models interact with language.
So it's a journey of continuous learning, both for the LLMs and for the humans who are learning to communicate with them effectively.
Exactly. And with that, we've reached the end of our deep dive into LLM training. It's been a fascinating journey exploring the intricate process of how these powerful models, acquire their language skills.
I couldn't agree more. From the initial data deluge to the nuanced techniques of prompt engineering, we've covered a lot of ground. I feel like I've gained a whole new appreciation for the complexity and potential of this technology.
It's an exciting field with incredible possibilities, but as with any powerful tool, it's essential to use LLMs responsibly and ethically.
Absolutely. And on that note, we'll wrap up this episode. Until next time. Keep exploring, keep learning, and keep pushing the boundaries of what's possible with these incredible language models. 282Ks.